Good morning. Today we'll be presenting our multi-stage robotic collaboration for automated block manipulation and palletization, which integrates two UR5E robots, a FANUC M1IA dual conveyor and vision system, and a PLC for full system coordination. Our goal was to design a fully autonomous palletizing workflow with reliable communication and consistent material flow across all systems.
The objective of this project was to create a fully automated work cell capable of continuous palletization with minimal human intervention. To achieve this, we integrated multiple robots and conveyors, all coordinated through an Arduino Opta PLC over Modbus TCP. The system needed to detect, transport, pair, and palletize cubes while handling timing, state transitions, and error-free synchronization. Our target behavior was a run forever operation, where each component seamlessly feeds into the next.
The UR5E number 1 uses vision to pick scattered cubes and places them on the conveyor 1. The conveyors transfer material to UR5E number 2, which works in pairs to load cubes into the feeder chute. The FANUC M1IA robot then palletizes them. Overseeing all of this is the PLC, which manages communication, timing, material counting, and the state machine. The system depends on each part performing its role reliably and in sync.
UR5E number 1 handles the initial detection and grasping of cubes using a Plock 2D camera. One key advantage of this approach is that cubes don't need to be aligned. The robot computes pick positions from the vision data. After configuring the Plock job, UR5E number 1 reliably picked cubes, even with variations in orientation and spacing. This step ensures the rest of the system receives a consistent flow of material.
The conveyors form the bridge between the two UR5E robots. Conveyor 2 is driven by UR5E number 2's commands, while conveyor 1 mirrors that behavior through the PLC. Critically, conveyor 2 automatically pauses if UR5E number 2 does not read to pick. This prevented dropped cubes and maintained a steady flow.
UR5E number 2 receives cubes arriving on conveyor 2. Its role is to pick 2 cubes at a time and load them into the FANUC feeder chute. This required careful tuning of approach points and gripping strategies, especially because cubes might rotate slightly on the conveyor. Through iterative collaboration, UR5E number 2 consistently performed dual picks and placed them accurately into the chute, enabling the FANUC robot to work efficiently.
The FANUC performs the final palletizing task using vacuum suction. It picks cubes from the chute and places them accordingly to the pallet pattern defined in RoboGuide. We used nesting loops and position-based offsets to generate flexible pallet layouts. The PLC signals the FANUC when cubes are ready and when the pallet is complete. Once the pallet reaches capacity, the FANUC halts automatically until the operator loads the next pallet to trigger a reset.
The PLC acts as the central brain for the entire work cell. All robots and conveyors communicate with it via the Modbus TCP. The PLC maintains counters for material flow, tracks ready for pick and picked events, manages run/stop transitions, mirrors conveyor speeds, and drives status light indicators. Its logic is written in structured text and uses rising edge detection to avoid double counting or unstable triggering. Without the PLC, all coordination would fail.
The system is governed by a compact run-stop state machine. The PLC tracks whether the system is running, whether a pallet is complete, and whether a new pallet request has been issued. When the FANUC reaches the pallet limit, the PLC transitions to FANUC stop and signals the robot to halt. A new pallet switch triggers a transition back to run. Clearing counters is needed. The PLC uses TON timers to generate clean one-shot pulses for FANUC start and stop signals. The button on the physical PLC can be used to halt the full program, including the URs and the conveyors.
Once all subsystems were connected and tuned, the work cell operated in a stable, continuous loop. UR5E number 1 detected and picked cubes, the conveyors transferred them, UR5E number 2 paired and loaded the feeder, and FANUC built the pallet, all without manual intervention. Integration required resolving timing mismatches, position offsets, and communication mistiming, but once resolved, the system behaved predictably and reliably.
The results show consistent performance across all systems. The UR5E1 reliably detected and picked cubes using vision. UR5E2 paired and loaded cubes with high accuracy. The FANUC robot produced clean, repeatable pallet patterns, and most importantly, the PLC kept everything synchronized, ensuring smooth and uninterrupted material flow. This demonstrates the effectiveness of multi-robot coordination in a real industrial workflow.
We encountered several challenges during development. Gripper alignment required repeated tuning, especially for UR5E number 2. Conveyor timing had to be adjusted to prevent collisions or dropped cubes. Small offset corrections were needed for accurate FANUC placements, and PLC debugging was the most time-intensive due to necessitated additions of event-driven logic and edge detection. Future improvements include adding feeder sensors, more robust error handling states, and speeding up the initial cube picking and placing on the conveyor.
The project highlighted the complexity of coordinating various robots, vision systems, conveyors, and a PLC. Modbus synchronization and event-driven logic were essential for reliability. We also learned how design decisions in one subsystem influence the entire workflow. Ultimately, successful automation requires not just mechanical performance, but also communication, timing, and software consistency.
In conclusion, we successfully implemented a fully automated multi-robot work cell capable of continuous palletizing. The integration of vision, conveyors, robots, and PLC logic allowed the system to function as a unified whole. The project demonstrated the value of multi-system coordination in modern automation and provides a strong foundation for scaling to more complex industrial workflows. Questions?